Okay. Let us begin again. So, is there any question before we begin? Okay. So we were discussing, right? Conditioning, right? Conditional distribution, to be precise, right? So we, of course, have talked about conditional probability, right? Or you supposed to have learned about conditional probability in math theory, right? Sorry, theory of probability, right? But here we take it one step further, or if you have seen this in theory of probability, that's great. But usually these kind of materials are not covered, right? Or sort of talked at the end and not covered in depth. So several things, right? The first reason, of course, is that like stochastic process uses conditional distribution all the time, right? That's where what they do. So it's just a step beyond, right? Let's say the basic, right, conditional probability that math theory of probability uses. But furthermore, right, basically the idea of conditional expectation and conditional variance is of crucial importance, right, for us to move forward. And you'll see, right, that the next lecture, lecture 5, is exactly used to, kind of is about kind of leveraging, right, these tools to find expectation, right, and variance by conditioning. Anyway, right, so what's the main point? The main point is, right, that basically given two random variables, right, we can define conditional distribution of x given y, right? Now, this actually is true in general, okay? X given y makes sense in general, meaning that, I don't even care what type of random variables x and y are. If you give me two random variables x and y, it makes sense for me to talk about x given y, all right? Again, what does it mean? It just means that I have the knowledge, right, of the value of the random variable y, right? I know what value it is. So you think of it as a history, right? And then based on that information, I want to deduce or I want to think about the likelihood, right, of the remaining one, which is x. Okay, that question makes sense in general, right? But the mathematics, right, required to make this precise, right, is let's say complex, and that's why we kind of kind of separate that, right, into the jointly discrete and jointly continuous case. Okay, but that doesn't capture everything, because as you see, right, that there will be cases where one of them is continuous, one of them is discrete, rare, right? But it happens anyway, right? But this is the main point in general. But if you have, right, let's say the case where that is given by formula, then you just follow the formula, right? Basically use the conditional probability kind of rule definition, right? But that's not it, because if you just follow the definition, you're missing out on the entire point, or you're missing out on the big picture. The big picture is that, right, in this formula, right, the role of x and y are very different. Y is treated as fixed. All right, this is the information that we're given, right? Fixed y, and x is the moving variable. Okay, x is the moving variable. So basically, we can abstract away from that x to put it as a dot. Okay, so for a fixed y, right, this whole thing is a distribution, meaning it satisfies the law of probability, right? Now, usually, right, usually this is not recognizable. What do I mean by that? Not recognizable doesn't mean that you don't even know what it looks like. No, you have a formula for it. But not recognizable as in like, okay, you cannot say that it's a binomial, it's a Poisson, it's something that you have seen before, right? Not recognizable in that sense, cannot be typecasted, right? Because of course, we only learned a few random variables as well, right? The models, the possible models are unlimited, okay? But the problem set, right? The problem set basically kind of, right, deals with very stylized case or special case, right? Where, right, that the conditional distribution can be reduced to a known, right? A known distribution. For example, here is hypergeometric, right? So the problem set, right, does not deviate from the theme of the lecture. Actually, it makes the theme of the lecture clearer. But having said that, right, we want to kind of caution, right, and say that, well, you know, basically, right, not all real life examples will be as nice as this. But, you know, in a classroom context, and even in a classroom context, right, you will not always see this. But, you know, we do some of the smaller problems, right, nicer problems to illustrate the idea, okay? And what idea are we trying to say here? Well, it's not really about this only, that basically conditioned, right? You have a nice result. No, it's not the only idea. The what we're after, right, is the conditional expectation and the law of conditional expectation, right, the law of double expectation, and, right, the conditional variance, the law of total variance, right? These are what we're after. And, right, as you can see, okay, basically the idea is if we don't recognize what this is, calculation of this will be tedious because you can only do it by formula, right? And, well, right, no one has time to sit around and do something by formula that doesn't have any nice pattern to look at. So that's a motivation, right, for us to look at these problems, okay? But to emphasize, right, of course, conditional distribution, all right, as an abstract concept is very important for us. You have to understand that. Now, from there, right, you need to understand how to go from, let's say, here to here by formula, right? So in case that is not recognizable or is not, let's say, it's not a something, you know, again, cool, right, it's simple, then you still can do the calculation, right? And then you can plug into a computer and let the computer give you the answer, right, the numerical answer, right? But in the case that is nice, like in this kind of classroom context, then we can push further, right, and demonstrate ideas. But before we continue, right, with these problems, with this problem number 2, right, let us kind of, again, look at the formulas, right? So the formulas, oh, sorry, I'm looking at lecture for a different class, sorry. Right, so the formula, right, for conditional expectation, right, is just like expectation. You see, look at this, right? Expectation is a sum of all the values over the probabilities, right? But it's very intuitive. Instead of having, right, regular probability, right, you have conditional probabilities, which will match conditional expectation. This is what we mean by, right, doing it by definition or by formula, right? Meaning that you have nothing nice to recognize, right, what this sum is. But the problem set that we do, right, have a nice recognition. So we don't have to, we bypass the formula, if you will, right? And we'll go back to this later. This is the, you know, the continuous case. The formula for, and conditional expectation, right? If you just have to remember that it acts like expectation, okay? Every rule that expectation follows, conditional expectation follows. Again, might sound new or exotic or something. It is not. The reason, right, it's just really a different type of expectation, okay? You should look at it that way. The materials we're doing is more complex, more advanced, but it's built upon, right, theory of probability. So it cannot deviate, right, from that abstract law. So if you understand the abstract law, right, then you know, any new case can be deduced back. You need to understand what's different and what's not. Conditional expectation is still an expectation. Therefore, right, any rules that apply to expectation will apply to it. Now, right, of course, the main difference, right, you have to remember is that even though expectation, right, is a number, conditional expectation is a random variable, right? Because you are conditioning on y. So it's a function of y. As a function of what you're conditioning on, right? That's the main difference. So whatever you do that violates this recognition, then that's wrong. But otherwise, right, here, notice that what we're dealing with here, right, this operation is operating on the x part or the y part, right? It doesn't touch the z part, right? The z part is there, right, for the show, and that's why, right, it holds. Okay. Yeah, right. We'll talk more about this later, as in like the proof, right? But conditional variance, right, works in the same way. In other words, right, basically, first of all, right, variance is expectation subtracting the mean squared, right? This is like the classical definition of variance, right? Variance of x is expectation of x minus mu squared, right? Where mu is expectation of x. That's what it's describing here, right? Except you see that, right? There's conditioning tagging along everywhere. And notice the inside here is also conditional expectation. And that's a very easy mistake to make, right? You could write this expression as expectation of x minus mu squared condition on y. This is wrong. Because what you do here is you plug in the mu, which is the unconditional expectation, right? For the kind of like the average here. Because you're conditioning on y. Everything, right, has to be conditioned on y in that context, including the expectation that you plug in to measure, right, the deviation of x away from it. Does that make sense? Any question about this? All right. But otherwise, right, then you can also do the simplified version, meaning that, right, if you have expectation of the square like this, okay, then expectation, then variance of, I guess I just mentioned this, but, oh yeah, right here, right, exactly here. You can recover it, right? Variance is expectation to the squared minus the square of expectation, right? But notice this is the square of conditional expectation, okay, for example. Again, all these are formulas, right? And unfortunately, or fortunately, depends on how you look at it, our problem set doesn't really go into these formulas that much. Again, for good reason, right? These are tedious formulas, but you have to be aware that they are in the background, right, of what we're doing. We're doing like a clean, nice versions of these where you bypass the formulas to demonstrate ideas, right? But that doesn't mean that ideas are not there. And then, right, what we're after is the law of total variance, right? The law of total variance. Okay, variance is variance of expectation, variance of conditional expectation plus expectation of conditional variance. All right, very important. And again, right, most people don't know this or miss this, or right, invent some weird formula like this. Right? And you can see where this comes from, right? This comes from sort of like a, who knows, right? Inspiration from the law of double expectation, right? So, okay, you have the law of double expectation, so you should have the law of double variance. Well, it doesn't work that way, right? So again, we'll talk about this, but that's why you need to be kind of, you need to go to class, right? To recognize that, or at least to be aware of what rule is correct and what rule is not, right? And why is this so? Okay, and we'll proceed with this next. Okay, any question? All right, so we were here, right? And this problem is educational in many ways. Of course, it is illustrating, right, that the conditional distribution, conditional expectation, conditional variance formula But there is another idea that is not kind of like currently discussed, but it's actually kind of giving you a very important result about the so-called Poisson process. All right, here we're dealing with Poisson random variable, but when people talk about Poisson process, right, they also can distinguish the Poisson process into different types, right, of events. And if you distinguish the Poisson process into different types of events, right, like male, female, or different colors and whatnot, then individual type, right, also follows a Poisson process. And that's the main idea here. But also that's the main idea, but that's the advanced idea here, right? That's embedded in this problem. But for now, right, we're just doing the kind of the baby version of it, right, where we look at the Poisson types, right, and kind of see how it works. And so to remind ourselves, right, we did the calculation last time, okay, and draw the conclusion that this conditional distribution is a binomial, right, with the total number of trials being the total number of arrivals, and the success probability being the ratio, right, of the rate of arrival of the first type, right? Because I guess we're looking at first type over the total rate of arrival, right? And I think that's where we stopped, right? And so B and C, right? Of course, is built on A, all right? So maybe, right? It's easy, but so let's see, right? Since we took a long break, let's see if we remember our probability, right? What should the answer to B and C be? If we have the conditional distribution like this, right, as a binomial, then what should the conditional expectation and conditional variance be?
The expectation would be n times p, where n is x1 plus x2, and p is the second part of the binomial distribution.
Good, right? So, and you should not use n, right? Again, I think we talked about this last time. N is fine up to this stage, but n will not help you to do the last part, right? So x1 plus x2 is good, okay? And the variance would be? Variance of binomial is np1 minus p, right? So it will be correct? Any question about this? All right. So now, right, the hallmark of all these calculations is that it should be consistent, right, with the law of expectation and law of variance. Again, right, notice here is not that we don't know expectation of x1 and variance of x1, right? We know what the answers are, right? The answers are lambda 1, right, in both cases, correct? But that's not the point. The point is somehow when we work out the right-hand side, we will get lambda 1, okay? Hence verifying these laws in this simple case. Okay, let's see, right? If we take expectation of B, do we see that we get lambda 1? Is that clear for us for the first part? so I don't have to write down. Right? If we take expectation of B, we get lambda 1, right? That should be clear. Agreed? Okay. So now, right, let's verify this one because it's actually a long formula, right? Remember, it's expectation of conditional variance and variance of conditional expectation. So let's write that in a separate slide, right? Variance is expectation of conditional variance. So here we're doing x1 plus x2, and then variance of conditional expectation. Okay. We have worked out, right, that is this so? Correct? Okay, so these are the inner expressions, right? Now we will plug them in where they belong. So notice this guy goes in here where we take the variance of this, right? All right, so tell me, if we take the variance of this, right, what would this term be? Remember, right, x1 and x2 are Poisson, right? Lambda 1 plus lambda, Poisson lambda I. Okay, so if we take the variance of that expression of the condition expectation, what should the expression be? You can go ahead and simplify. What should, yeah, go ahead.
So variance isn't linear, so you would have lambda 1 over lambda 1 plus lambda 2, that constant squared,
Good.
times the variance of x1 plus x2, and by the distribution, we know that is lambda 1 plus lambda 2.
Excellent.
Canceling terms, we have lambda 1 squared divided by just lambda 1 plus lambda 2.
Perfect. Perfect. All right. So I'll say that one more time. So, right, when we take the variance of this, right, this constant comes out as a squared, right? And then variance of this is lambda 1 plus lambda 2. So when you simplify, right, one of that cancel, but lambda 1 on top is still lambda 1 squared. Are we okay with this? Okay, what about the first term? When we take expectation, what would that be? That should be simpler, right? For the first term, right, clearly, if we take expectation of this, you got lambda 1 plus lambda 2, right? Cancel with one time, leaving us with lambda 1, lambda 2 over lambda 1 plus lambda 2. Agreed? Now, do we see that if we add these two together, we get lambda 1? Yes, right? And that should finish that. Any question? All right, so let us continue to problem 3. So this should be reviewed as sort of like the other side, right, of the yoga-stereo problem. That's why it's called yoga-stereo problem part 2. By the way, right, there's nothing yoga, right, about this problem. It's really about Poisson, right, arrival stream. But this is from Ross, right? If you look at the textbook, what he calls that, he phrases it as a yoga-stereo, right, attendance. So yeah, I'm just following the spirit, right? But really about Poisson stream arrival. But notice, right, for the previous ones, you have the individual types, namely the male and female, right, given as Poissons. Now you have the total type, right? Meaning the total arrival given as a Poisson. And now you have the success probability of each type. But notice, right, the word success probability here is very, very close to exactly is the binomial that we looked at in the previous problem, right? It's just basically which side you start from. The results are always consistent, right? And that's why it's called Yoga-Steele problem part 2. But it exactly illustrates the same phenomenon, just looking at from a different point of view. Okay, so what are we looking at? We want to find a joint distribution of males, females, right? So if we let x1 be the number of male, x2 be number of female, right? Then what we're looking for is probably x1 equals to I and x2 equals to j. That's the question. Okay. Now tell me, how can you accomplish this with the information of the problem? Well, given the total, right, number of arrivals, right, as a distribution, as a Poisson. So what are we given, by the way? Let's write that down, right? We're given what? We're given that x1 plus x2 is a Poisson lambda. All right. What else? How do we interpret the p and 1 minus p information?
Can we first observe that x1 is independent of x2?
No, incorrect. Very much incorrect. That's not an observation. You're right. Intuitively, it feels like they're independent, but that will come as a consequence of our calculation.
Okay.
Meaning, right, that somehow, you see, at the end of this calculation, we will get something like this. Or we get that basically, right, in terms of math, the I expression and the J expressions are split. All right. And that's the proof that they're independent. It's really a icky business, and this dates back to 477, which, you know, like, well, I guess you didn't take with me, which is fine, right? But I emphasized back then that independence is either an assumption, meaning that the problem put it there, like blatantly, right? This is independent, or it has to be deduced from the information of the problem, meaning that the calculation show that the expression split. There's no such thing as, well, must be that these are independent, therefore, etc. You see what I'm trying to say? It is something that is in our habit of throwing it in to make things easy for us, right? But one, it may be not justified, meaning that it's already there, but it's not the way you're supposed to be. Or B, worse, it could be wrong, meaning that they're not independent, or you just assume they are, right? So here, you're right. That feels like, or it should be, they're independent. But like I said, you'll see, right? It will be as a consequence, not as a starting point.
That makes sense. Okay.
So where do we start? Or let's repeat, right? With the p and 1 minus p, right? What does that mean? Notice, right? The p talks about individual people, right? Individual person. It doesn't talk about the total, right? X1 is total, right? Total male and female. So how do we resolve that?
We could say that x1 and x2 are both binomial.
Incorrect. Completely incorrect. No. That's exactly where the conditional statement is very subtle. X1 and x2 are not binomials. Think of it. Here's a reason. First of all, right, when you say a binomial, what's a main characteristic of a binomial?
Oh, that each of the Bernoulli trials are IID. So that's
No, not about that.
okay.
Here's in this case, right, a binomial, the most blatant characteristic in this problem compared to the context is that a binomial has an upper bound, isn't it? A binomial can only go so high. Agree? Like a binomial 10p, right? That's why we always have to name the parameters. A binomial cannot go forever. Agreed? It goes up to a finite point. Now tell me, does x1 have an upper bound here?
No, because a Poisson distribution is characterized by an unbounded
Right, but that's x1 plus x2, right? But by consequence, x1 also has no upper bound. Agreed?
Right.
Therefore, clearly, x1 cannot be a binomial. Now, of course, the binomial is in the air, right? You're not wrong to think of a binomial, but what's the right statement? The right statement is x1 condition on x1 plus x2 is a binomial. Understand the difference? Once you fix the sum, then you have an upper bound for x1. But you don't fix the sum, meaning you say x1 alone, then it's not a binomial. So this is a binomial x1 plus x2 p. And that's exactly the subtle statement that you have to recognize, right? And then x2 condition x1 plus x2 is binomial x1 plus x2, 1 minus p. Do we understand? Any questions? All right. So now I have shown you, right, all the given information. How do we leverage that to calculate the joint distribution of x1 and x2? We have the conditional distribution, and we have this, and we want to calculate this. This is clearly a call for the law of total probability. Agree? Oh, sorry, it's not even the law of total probability, but what do we put here? It's actually just conditioning and give it back, right? So here it will be condition on x1 plus x2 equals to I plus j, right? Of course, because if x1 is I, x2 is j, x1 plus x2 must be I plus j, right? So even though it sounds like that in terms of logic, we don't get anything more. Notice in terms of the behavior, distribution-wise, this is very different from the unconditional one. You understand? All right, so now we plug in, right? So, okay, actually, and by the way, right, here, you mentioned the word independent, right? Here, actually here is where you can use the word independent, you can use independent here in the assumption. This is fine. In other words, right? So let me say this. These are conditional independent. Meaning that if you condition on the sum, then x1 and x2, right, individually behaves independently as binomial. That's actually part of this assumption. But x1 and x2, right, unconditionally, it's unclear that we're independent, right? So there's that idea of independent versus conditional independent that I put in the slide. I don't think we have time to go over that. That's really a fine point. You can read it for yourself, right? But my point being is, right, when I say is we cannot assume they're independent, that I'm talking about the unconditional version. Condition, right? Then yes, we can use independence here. Is that okay? Does that make sense? Because it's part of the assumption of the problem. The problem says that, right? Person is male, or probably P, right? And the person is female, probably one minus P. I guess, of course, right, independently, it can be either male or female. Do we understand all these points? All these assumptions, how they fit in, where I use them and where I don't use them, and why? Okay, right, now let's plug in. So because these are independent, right, I can split them. So notice binomial, right? So it will be I plus j choose I, right? For the, oh, by the way, right? So for example, you know what? I'm stupid. Sorry, I think I go too much. I don't even need to do that because, right? Let me just do one more. Sorry, I don't even need that. Sorry. Notice, right? Let's simplify one more time. What does this reduce to? This will reduce to, this will simplify to x1 equals to I, condition on x1 plus x2 equals to I plus j times this. In other words, I drop this going down here. You see that? You see why I can drop that?
Could you explain?
Sure, but there's nothing to explain really because, right, if I already know that x1 plus x2 is I plus j, and if I know x1 equals to I, does it automatically follow? Meaning that this actually is a sub event of this. If I know that the sum is I plus j. If I don't, I cannot drop them. Meaning, right, I cannot drop it here. They're wrong. This and that are not the same. But if I know the sum, then, and I know one of them, then I don't care for the other. And again, right, this problem demonstrates the subtlety of conditioning or using the information you have access to. Like the information changes the picture a lot, all right? And you could use it wrong a lot of times, but you know, you just learn, right? But yeah, so right, this is why I keep saying the conditioning is not easy business, right? But this is one of it. If I know the sum, then I can drop one of the term because, right, if I have the sum, I can deduce the other term. If I don't know the sum, I have to keep both terms.
I understand your reasoning, but would it be wrong to do it the other way where we split
Oh, you mean the? Of course not. If my reasoning is correct at all, then they must be the same. This must be the same.
no,
right?
that's not what I meant. I meant originally, like, we thought we could use the fact that they're both x1 and x2 are conditionally independent to split the.
Oh no, that would be wrong. That would absolutely
Okay,
wrong. So I was yapping on that for no reason. The reason is, right, these are not two pieces of information. They're one piece.
Okay.
So that's why, yeah, I was talking nonsense for a while there. I mean, they are, but that's not this kind. No, and in fact, sorry. Actually, that statement is blatantly wrong. I deeply apologize. Right, that statement is deeply wrong. Sorry, x1
Okay.
and x2 are not conditionally independent given x1 plus x2. Sorry. You see why? Because if I know x1 plus x2, right, and I know x1, x2 must be deduced, so they cannot be independent.
Oh,
so
that
sorry.
makes sense. Okay.
No, that statement is complete nonsense.
I
Actually.
thought they would be conditionally independent because x1 counts the number of
No, you see, that's exactly, again, right? Our mind wants to go in a certain way. I
Right.
want to push the independence. And I guess you mentioned the word independence. So I kind of want to go there. But when you kind of step back and stay a little bit clear-minded, no, that's complete nonsense, right? Because like I said here, right? You see, if I know x1, then x2 are completely determined given x1 plus x2. So how can they be independent? Agree? So if we drive there, it's actually completely nonsense, actually. It's blatantly wrong. So yeah, sorry for that. That statement is completely wrong. Is that okay?
Yes, that makes sense.
Okay. So now, right, let's continue. So this will be I plus j choose I, p to the I, 1 minus p to the j, right? And this will be Poisson, right? Poisson lambda. So e to the minus lambda, lambda to I plus j over I plus j factorial. Okay. Any question about this so far? All right, so now we need to simplify, right? Because these are the nice problems in this called Yoga Studio, so it should have something nicer than this. So how do we simplify this?
From the choose notation, if we express it as a factorial, I'm sure cancel the I plus j factorial.
Correct. So we have 1 over I factorial, 1 over j factorial. That's correct. Right. What else? What can we do here? Again, right, the hint is we intuitively want to separate the i's and the j's, right? We want to keep the I together. We'll keep the j together. Look at the expression and see how that drives the calculation.
You could split the lambda in the numerator and say lambda times p to the power of I. And
Correct.
similarly for the j term. So 1 minus p times lambda to the power of j. And they get stuck in the middle.
Good. Right. What seems to be missing here then?
Just the e term,
Okay, so how can we do that?
which knows no side. So you could just multiply it on to either term.
Meaning,
No, either factor.
what do we mean by that? So how do we write the e term?
Just e to the power of negative lambda times the first factor times the second factor. The ith factor times the jth factor.
Oh, like that? Okay,
Yeah.
but is that meaningful? I mean, that's not wrong, but is it meaningful? Do we recognize what that is? I mean, what does this look like, or what does it look like it want to be?
Oh, actually, you could actually split the e to the negative lambda along
Correct.
the lines of
Good.
p
Exactly.
minus p,
Mm-hmm.
because
Good.
then it would look like a product of two marginal Poisson distributions.
Which it is, right? This exactly is Poisson. This is Poisson, which, like I said, right, that's why they're independent. So x1 is Poisson, lambda p, x2 is Poisson, lambda 1 minus p, and they're independent. All from this calculation. Notice, right? No assumption. No assumption at all.
In an exam, is it safe to assume is it safe to not assume independence unless it's explicitly given in the problem statement?
Absolutely, right?
Okay.
That's the whole point, right? And again, you see, you could really say something nonsense because they're not, right? So no, absolutely not, right? I mean, that's the whole point, right? Correct. I mean, not that you should not use independence, but it's one of those things where you have to ask if is your mind just really craving for it, or is it really there, right? So, and again, right, I hope you see why here it's not really there, right? No one says they are independent, and you see it comes from the calculation. Okay, so as far as let's say this problem is concerned, I hope that that gives you an example of that, right? Okay, any question? All right, let us look at this one. Okay, any guess? And right, the hint exactly gives you the interpretation, right, of this problem. Now, of course, right, let's just say this, right? Let's say this, so they want you to kind of do it by intuition, right, or by conditional thinking. That's what they're doing here, right? Which is really something we promote in this class. But let's say, right, what's a way to do this without having to do conditional thinking? Is it that impossible to do this without think? What can we do?
Can you rewrite that as the joint over the marginal?
Yeah, right. I mean, if you really don't have a clue, you could just do this. Why? Because, right, all this are actually easy to calculate, right? For example, why? Because we have x1, x2 are independent geometric, right? So the top will be what? P to I minus 1 times 1, sorry, 1 minus P, right? Times P, agree? And then 1 minus P to the n minus I minus 1, right? Times, sorry, times P, correct? And then the denominator will be what?
It's a negative binomial, right?
Correct. So it's n choose 1, right? And then 1 minus P to the n minus 2 times P squared. Agree? So when all the dust settles, what does it look like? Looks to me like 1 over n, right? I mean, not a question mark, but that's 1 over n. So now that we see that, is that clear? Do we see that like that or no? Oh, sorry, it's not n choose 1, sorry. It's n minus 1 choose 1, sorry. There's an error here, right? A negative binomial from the previous trial, you choose, right, k. So 1 over n minus 1. Is that clear? So to answer, right, what is the answer here? The answer here, right, is that it is a uniform, right? The condition distribution, x1 condition x1 plus x2 is a uniform, a discrete uniform, right? With values from 1 to x1 plus x2 minus 1. Okay. Now, why so? So here, right, I would probably value the calculation, right? The intuition probably comes later. But the intuition, right, is like this. If you, like I said, right, you toss a coin, right? Tail, 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 whatever, and then head. And then, right, tail, tail, and then head, right? You get a second head. But this, right, all you know, right, is that okay, the second head appears at the nth row, right? The 10th row, let's say, right? And you wonder where the first head would be, right? In the previous, let's say, 9th row. You think about it, right? There's no favor information, correct? About where the first head should land. It could land equally, right? Among the first 9 rows. Agreed? I mean, in this geometric, and that's sort of like the tricky thing. This coin is biased, right? Its head would probably P, tail would probably 1 minus P, right? So it's not a fair coin. If it's a fair coin, probably would say, well, yeah, that's whatever. But it's an unfair coin. Yet, condition on the position of the second head, the first second head, right? Then the first head will be equally likely among the first n minus 1 term. Think about it. Again, I have to say that makes perfect sense to me, right? But can I come up with that intuition when I first read this? Maybe not. The calculation helps me out here. All right. So again, it's tricky. All right. Any question? All right. So yeah, I just have to do the calculation. All right. So I think it's time for the quiz. All right. Yeah, let's have you do 1A, right, for the quiz. Just 1A, okay? I want all calculation. I want all calculations, okay? All right. Any question before I turn off the camera and the voice? All right. So we'll continue in 10 minutes, all right? Okay, let us start again. Any questions before we continue? All right, so this is where I want to stop. Problem set 4. I mean, as you can see, there are more problems, but you know, we have a lot of materials to cover, and I think it's kind of the flow. We should continue with new materials, right, to get to Markov chain in time. So I will send, I will update the homework set, to include, you know, the problems, we discussed here, to update the homework for problems. So for the midterm of this Friday, the materials will cover homework 1 to homework 4, as kind of stated here, meaning the problems will be based on the ones that we went over in the homework. Okay, 1 to 4. Again, I'll also send an announcement about that later on today. Now, having said that, as you can see, the materials in this lecture 4, we kind of barely scratched it. There are tons of materials, namely the sort of the version of conditional distribution for continuous random variables or mixed. It's kind of in here. We did not discuss the proof of, you know, the law of total variance and law of double expectation. Did not discuss. Also, the very important sort of notion of conditional independence versus independence also did not discuss. I mean, if this is a more in-depth course in probability, we'll go over this, but this is a course in stochastic process, so we'll kind of continue. But so if we don't cover the materials, it won't explicitly show on the exam. That's for sure. But that doesn't mean, that these concepts I wrote down here, will not be relevant. That's a double negative, meaning that, the materials here, even though we didn't go over, we didn't have time to go over, might still be relevant, okay, for later materials. But if I skip them, that sort of means that, you know, they might show up less frequently or, you know, whatever. So if we encounter them, we might go back and talk about them more. But having said that, you're strongly encouraged to kind of go over the slides and look at the extra materials, if you're kind of motivated to learn these materials completely. If not, I mean, if you want to prep for the exams and things like that, the homework materials, are what you should focus on. Okay. Any question about this?
So what lectures will correspond to the midterm?
I think also lecture 1 to 4, I mean, okay. The problems are mirroring sequentially, to the lectures, I think. So yeah, I feel like they should be similar. But of course, the lecture materials are more, than the homework. So okay. So now moving on to next materials. All right. So in terms of where we are in the textbook, we are at the end of chapter 3, okay? And again, after this, we will definitely cover Markov chain. But this is a very important material, and as you can see, the point I want to make here is that in some sense, we are covering probability, but stochastic process flavor, is strongly present, okay, in all these problems. So yes, we are doing stochastic process as well, if you want to look at it that way, like the Poisson problems we just did before, and you see, the problems we do here will be explicitly referenced again when we do the Markov chain, in terms of pattern tracking. So, but without further ado, the focus of this lecture, if you just want to look at the theme, is finding, right, expectation and variance by conditioning, right? And the point, right, is that, you know, calculating these are not easy business, okay? And formulas, right, alone may not help. Let me just give you an example, right? And again, we should have seen this before. Let's say X is a binomial, right, NP, okay? Expectation of X is the sum K from 0 to N, N choose K, P to K, 1 minus P to 1, N minus K, right, times K, right? So first question, is this correct? Is this a correct formula? Answer is yes, right? It is correct. How many points should one get for this if one write this as an answer on the exam? 1 out of 10, or, you know, if one feels generous, 2 out of 10 maybe. Why? Right? And this is where, right? I mean, I don't know, students always complain about grading for whatever reason. They completely miss the point, right? The point is not about being correct. I mean, correct has many meanings. They completely miss the point of the question. Of course, if it's a binomial NP, no one accepts this as an answer, right? It must be N times P, right? And of course, if you go from here to here and you kind of don't even recognize how transition goes, fine, whatever, right? But the point is that the answer expected is N times P, because we have, right, a simplified answer. Giving a complex answer is just not to the point. But of course, that begs the question of, right, how do we go from here to here? And the answer is, right, well, you could work with the combinatorics expression. It is not a fruitless exercise. It's a nice exercise for you to work through the combinatorics expression and see that it reduces to N times P, all right? But, right, there are other ways we can do it, namely using the indicator function, right, to get there too. So that's sort of like to encapsulate, right, sort of the point of math in general, or probability in particular in whatever we're doing. That, right, if you just kind of apply formulas and definitions, blah, 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 that might work at a calculus level or even below that, right? You might earn points. At a more advanced class, right, the point is you have to know what you're doing. You have to know what answers we're looking for, right? What structure we're working with, that kind of thing, right? Applying formulas alone is a machine business, right? I mean, a machine can do it as well as you do, so why do we bother? So, so we talked about using the indicator, right, random variable technique, right, in lecture 3. That's a very powerful technique to find expectation and variance, right? And we talked about it here, right? Where was it? The hat problem. Where was it? Oh, I forgot. Yeah, the hat problem, right? But a different approach, right, is to do conditioning, right? To use conditioning, right? Use the conditioning. So, for example, right, expectation of X given Y is expectation of X, right? Simple. And so in lecture 4, right, we introduce you to this idea, of course, with the variance too, right? I skipped the variance formula, but we know, you know what that is. Lecture 4, we introduce you to this formula and demonstrate to you, hopefully convince you that it works. But, right, that's understanding the formula, playing around with the formula. Now you have to use the formula, right, which is the more advanced challenge. Meaning that now, right, you have to find the suitable Y to condition, right? And then to work out the expression. The problem is this, right? It's actually very similar to the problem of the indicator function technique. That there are more than one ways. There could be more than one ways to break it, right? Break a random variable into a sum. So similarly, right, the formula is valid for any kind of Y you want to condition on, right? The formula is valid. Doesn't matter what X and Y pair you pick, but picking the wrong random variable to condition on is meaningless, right? Picking the wrong random variable to condition on is meaningless, meaning that it will not help you simplify the answer. you won't get a nicer structure out of it, and then you're just gonna struggle, right? So the challenge in this lecture, or this lecture is not even a lecture, it's a lecture, but I'll just go through several examples, okay, to demonstrate to you the right way, right, to pick a random variable to condition on, right? And we'll just do a bunch of problems to demonstrate that. But the key is, right, or the challenge is to find the right random variable to condition on. Okay, so let's go straight to the point, right? You can read this, but let's look at the geometric, okay? So let's review this, right? If x is a geometric random variable, then we know expectation of x is 1 over p, right? What about variance of x? Does anyone know or remember the variance of x formula?
Isn't it 1 minus p over p squared?
Fantastic, great. Now, right, let's ask, who can prove this is true? Now let's see, right? If you follow the definition, expectation of x will be the sum, right? K from, you need one trial first, right? K equals to 1 to infinity of k times 1 minus p to the k minus 1 times p, right? And somehow this has to be equal to 1 over p. And expectation of x squared, right, is k from 1 to infinity, k squared minus p, k minus 1 times p, right? And somehow this has to be, right, if you look at this right here, right, is actually 1 over p squared minus 1 over p, right? So if you add that with, right, so it's going to be 2 over p squared minus 1 over p, right? Because expectation of the squared is variance plus the square of the expectation, right? Notice that both of these, again, there are analytical tools, right, to prove that this is true. Notably, the tools of kind of moving the differentiation operator inside the sum, right, which is a very nice tool in analysis. What we want to show you here, right, is the way to do it by indicator, right? By conditioning. Okay. So the point is, right, what should we condition on? And the variable we should condition on, call it y, whatever you want, right, is the result of first trial. All right. Because geometric, right, is about, right, tossing the coin until you see the first success. So just is intuitive, right, to condition on the first trial. Why? Because, right, let's see if we understand this. So y, right, is a Bernoulli random variable or an indicator function, right? So y can be either 1 or 0, right? So what is the x condition on y equals to 1? What would that be? If x, right, is the number of trials until we see the first success, x condition on y equals to 1 would be what? To be clear, right, y equals to 1 means the first trial is a success. Right, if x counts the number of trial until first success, the next condition y equals to 1 is?
Well, it's 1, right?
Is 1 identically, right? It's not even a random variable. But, we can count a constant as a, a special case of a random variable. Do you understand? On the other hand, right, what about x condition y equal to 0? What would that be? So here, right, is where we're getting into the idea of Markov chain. All right, this is the memoryless property, right? And you can think of this as a Markov chain, as in like, you know, is a special case, right? A very easy case where you just keep rolling, right? Every time you kind of roll, right, you kind of forget the past in a sense. So here's the thing, right? If the first trial is a failure, right? So if it's 1, then you stop. If it's a 0, well, what do? Well, you just kind of redo the whole thing, right? But if you redo the whole thing, what that means is that you cause an extra trial and you repeat the experiment again, right? So this is like the memoryless property, right? If you have, or Markov property, if you will, right? If you have had a failure, well, okay, just repeat the trial again, right? So maybe like Markov, right? Because there's some kind of memory here, right? The memory that you have had a failure. So maybe like a Markov property, right? You have had a failure, okay, right? Fine, then start from there again, right? And then continue. Is that okay? But anyway, right? The point is that this set up a recursion for us to solve for expectation invariance. And this is a common theme, all right, in this section, that basically once you find the right random variable to condition on, you basically see the same distribution repeating, right, using that conditioning by Markov property and things like that. And that basically, right, allow you to set a bootstrap equation, right, to solve a recursion equation, to solve for the variable you want. Okay, so let us demonstrate. So this, right, what we're listing here is what's the so-called conditional distribution, right, of x given y. All right, again, this is why lecture 4 is important, right? You have to understand what conditional distribution is. So here, right, we list the conditional distribution of x given y. But of course, we cannot give it generally in one swoop, right? Like the nice examples in the lecture, in the problem set 4, right? Here, depends on what values y take, the conditional distribution are very different. That's why we have to break it down to cases. Okay. Now, right, we will apply the formula expectation of conditional is expectation, right? I love the word expectation. So, right, now let's see what it means to execute this. So expectation, right, of x given y equals to 1 is, what should the answer be?
Just 1?
Correct. What about expectation of x given y equal to 0?
1 plus the expectation of x tilde.
Excellent. But because it's also a geometric, right? So that's exactly
right.
the same as the expectation of x, and that's where we get the recursion. All right. So now, right, we have done the inner expectation, if you will, right? Now the outer expectation, right? Let's see if we understand this. How do we do the outer expectation?
You have to sum over the values of y. So it's 1 times the quantity 1 plus 0 times the quantity. Wait,
Wrong.
never mind.
No, you're excellent there,
Sorry,
right?
sorry. You have to sum over the
well-
values of x, not the values
No.
of
The more you go, the more confused you are. You were correct. The outer expectation is over the y. You're very good on that. However, right, it's not over the values of y because it's
over
gonna
the
be over.
probability distribution.
Correct. So
Right,
it will
got
be 1 times
1.
1 times the probability of y equals to 1 because it's over the distribution of y.
Oh, that makes sense. Okay.
So 1 times p plus 1 plus ex times 1 minus p. This is probably y equals to 1. This is probably y equal to 0. So, right, the values are the values of the condition of rotation. The distribution, remember, right, is a random variable. Is a random variable depending on y. That doesn't mean the value, right, is derived from y. The value is derived from the function of y, which we just calculate. But the distribution is the distribution of y. You understand? And so, right, this must be equal to expectation of x. All right. So, right, these steps right here are all very important to get to the final equation. Well, this is the equation, right, to be solved for EX. I mean, of course, solving it may not be, it's kind of assuming, but whatever, right? The point is, that's the step we want to get to, right? So you start with finding the right random variable to condition on, meaning determining what y is. Then you have to think about the conditional distribution of x given y. Why is that? Because that is the crucial step for you to calculate conditional expectation. If you don't go through this step, you would get this wrong. And then, right, after you get this, you have to now consider the distribution of y so that you can take the outer expectation. So we're sort of like, right, we go from the inner to the outer expectation. Okay, any question here? But then, right, you see that this simplifies to 1 minus p, right, e to the x, right, and this is plus 1, right, is ex, correct? Right, so if you subtract on this side, you get pex is 1, or ex is 1 over p. Any question?
I'm a little bit confused about how you initially set up the recursion. Why did we get that x conditioned on y equals 0 equals 1 plus x tilde? Why did you
So
write it
this,
this way?
this has to do with the understanding of what this means, right? So again, x tracks the number of trials until we see the first success, correct, of independent trials. If the first trial is a failure, if we know that, then the total number of trials to see the first success can be viewed as 1 extra, because the first is a failure, and search again.
So what does x tilde represent, I guess?
X tilde represents the search after the first one. This is exactly the reset of the Markov chain.
Oh, okay.
Understand? If you have, again, right, just physically think about it. If you have to wait for the first head, and if the first trial is a tail, then what do? You redo, right? You just redo, meaning you restart a geometric random variable. But don't forget that you have already got a tail. So whatever you get after that, you just add 1 to it. Does that make sense? This idea of repeating, right, the experiment comes back in the same distribution is a very, very powerful tool, or is a very, very powerful idea in Markov chain, right? Basically, once you go back to the original place, whatever that means, you sort of have a reset, right? A soft reset. I mean, basically, as far as the chain goes, right? As far as like searching for the first success goes, you just restart from scratch. But of course, your memory, right? If you're tracking the total number of trials, then you have already taken 1 extra step to do it. So that's why it's 1 plus.
That makes sense. Thank you.
And it's x tilde and it's not x, right? And I think that's the last common mistake. Is right, an x here would be nonsense. Nonsense in the sense that x is already here. X cannot be 1 plus x, right? So x tilde represents, of course, a different count, but distributionally, it behaves the same as x. Now that's why, right? We say x tilde is geometric p. That's why it's a reset. Any question? Any other question? All right, so now let's look at the variance. Variance calculation, right, as a warning, is always more complex, and you have to be very careful when you do it. So variance, right, is expectation of the conditional variance plus the variance of conditional expectation. All right. So let's see here. Maybe let's kind of see if you have a feel for this problem. There are two terms here. Which term might be easier to calculate given what we've done so far?
Because we kind of already know the conditional expectation, it's easier to calculate the second one, I would guess, because we know the inner term.
Okay, yep. So let's take a look, right? So expectation of x given y. 1 second, let me try to think. You have a good intuition there, I think, but there could be. Hold on. Let me try to think. Is that true? So right, so the problem though, right, is expectation of x given y, right, is, let's say, right, is 1 with probability p, right, from here, and it's 1 plus expectation of x, right? Or we can do that now. We can replace it with
1 divided by
1 plus 1 over p, right? With probability 1 minus p, right? Okay. So now we want to calculate the variance of this random variable. Sorry. Okay. So let's talk about just basically the execution of it, right? What do we have to do here?
Can we identify
So we have to.
the distribution?
This is a distribution, right? So you have to write down like the expectation of the square minus the square expectation for this. You understand what I'm trying to say? You have to do p times 1 minus p times this, and then simplify, right? Okay. So here's a calculation trick. So let me just say, right? If you calculate directly, right, it will be something like this: 1 square times p plus 1 over p squared times 1 minus p minus 1 times p plus 1 over p times 1 minus p squared. Do you understand?
We already know the second term though, right? Because it's just 1 over p squared. Or no?
The second term, this one is 1 over p squared. I'm not so sure, right? At least it doesn't
Oh wait,
look
sorry,
like
no,
that.
never mind. You're right.
No, that's not about the final answer. No, the final answer has nothing with that right now, right? This is just about this random variable right here with this distribution. Does it make sense? So I'm just taking
Yes,
this
okay.
as. So basically, I'm just saying this is tedious, right, to unravel. And again, right, it's not the fault of the technique. It could be in the sense that the technique might lead you to a nasty calculation, right, or whatever. But be prepared for this kind of thing. We can unravel this, right? But here's an easier way. Here's a trick, basically, for this one. Observe, right, in both of these terms, what happens? What do they have in common? A 1, right? So what can I do with that? I can subtract that away. right? But why? Because variance of a random variable is equal to variance of that random variable at a constant. Do you understand? All right. And now to even make it more, make it easier, right? I can do it one more time. This is 0 with, so this is exactly like 1 over p times a Bernoulli 1 minus p. This one is 1 over p times a Bernoulli 1 minus p. You see why? Because, right, 1 over p times a Bernoulli 1 minus p would be, right, 1 over p times 0 with probability p, and 1 over p times 1 with probability p. Oh, sorry. 0. Notice 1 minus p now is a success, right? So success is this. Yeah, correct. Right. You understand? So, right, it will be a variance of this, which will be 1 over p squared, right? And then p1 minus p. So that's this calculation. Any question? Okay. So now let's take a look at the other term, which is expectation of the variance, right? Conditional variance. So for this one, we need to know what the conditional variance is, right? So let's go back to here. What do you think the conditional variance of x given y is? Or let me be more, right, explicit. What's conditional variance of x given y equals to 1?
Zero?
Excellent, right? Because it's a constant. So conditional variance is 0. What about conditional variance of x given y equal to 0? So remember, right? If y is 0, then x behaves like 1 plus another version of itself. Therefore, conditional variance here is just variance of x. Do you understand? It's actually variance of 1 plus x tilde, but the constant, right, doesn't affect variance. So it's just variance of x tilde, which is variance of x. All right, any question about this? Therefore, right, expectation of conditional variance, this happens, right, when y equal to 0. So the answer is 1 minus p times variance of x. That's the second term. Sorry, that's the first term. Right, this term we have calculated out to be this. And this must be equal to variance of X. So you see, right? It means P1 minus P over P squared is P times variance of X, giving us variance of X is 1 minus P over P squared. All right, any question about this whole calculation? It's an advanced technique, right? Or, well, it's advanced to having seen this before. And yes, right now we're properly in the territory of 478, right? These are challenging materials, so ask questions.
Really quick question. Because X tilde and X both follow the same geometric
Distribution.
distribution, we can say that their variances and their expectations are equivalent.
Are the same, correct?
Same.
Absolutely. That's the whole point of having a repeat distribution. Notice X and X tilde are not independent, right? But they have the same distribution, and which we can leverage for our recursion. That's exactly it. In Markov chain, right, things are not independent in general. No, otherwise, right, things are so trivial. But you would usually have the same distribution repeating itself if, let's say, the Markov chain returns to the same place, same location. So, right, yeah, same distribution. Basically, same distribution implies same everything, same probability, same moment generating function, same variance, same expectation, same whatever. Of course, the only thing is that you cannot mix them together and look at the joint distribution and say that's a product. You cannot do that. But if they have the same distribution, whatever you can say about one, you can say about the other separately. Marginally, right? Marginally. Okay. So, right. So here is sort of like the, again, right? What we just talked about, but now kind of in slides, right? So, and this is exactly right, same distribution. That's the notation. So just showing that to you, right? Again. Okay. All good. All right. So is this the end of the story? You wish, right? This is just the beginning. So the general idea here is not even general yet. We'll have even more fun. We'll get to Markov chain. But you can see that this is like tracking time, right? To seeing a pattern. All right. And again, right, I'm saying, right, pay attention. We are doing stochastic processes here. There's time, there's pattern, this is actually what we're looking at in terms of Markov chain, in terms of stochastic process. The notion is called a stopping time. We're looking at the expectation of a stopping time. All right. Even though this is the first example we did is so simple, right? It's called geometric random variable, but it is a stopping time, right? In the literature of stochastic processes. Now we will make it much more interesting, right? And look at a pattern, right? But what's simple is here. We haven't done a non-IID sequence yet, which is a Markov chain. Markov chain will take this a step further because, right, Markov chain will take away the IID assumption, right? But if you just have like, okay, like a coin toss, right? So, yeah. Basically, right, I'll give you an example. Suppose that you toss a sequence of tail, tail, head, tail, tail, whatever, right? So this is an IID sequence, right? Because each of the coin toss, right, is a Bernoulli, right? P1 minus P, right? Let's say you want to find the first time. the first time you get two consecutive tails, or for that matter, right? Two consecutive heads, if you will, doesn't matter, right? What is the expectation? All right, forget the distribution. We just talk about expectation now. So the general remark is, right, find a suitable random variable to condition on to break the problem into more manageable parts, okay? And then, right, use the law of double expectation, right, you have to look at the conditional distribution, but, right, so basically find a random variable to condition on, and then, right, look at the conditional distribution. If, right, the random variable you choose is right random variable, that will break the problems into more manageable part. Or in other words, you should see a repeat of something you've known before. And then, right, you apply the law of double expectation from that point on. Okay. Okay. So let's see if so I think, right, this is just basically, right, showing you how a geometric random variable is a stopping time, is a time to first success, right? But the calculation we've seen before, just now recast as like a time, right? N1. N1 is the time to first success, right? All right. So there you go. Right. Oh, so here I want head, right? So now we want the time, right? It takes to see the first two successes. So first, let's talk about the notation, right? Minimum represents, right, the idea of first, right? And then this tells you it's consecutive. All right, and of course it's Bernoulli P, so it's ID trial. And we want to find expectation of N2. Okay. So now let's kind of say something obvious or not. Well, don't we know what N2 is already? Is an N2 a geometric, is a negative binomial? So we can just find its expectation, right, using the formula for the negative binomial expectation. Is this true? Is N2 as I define it here? Does N2, right, as I define it here, have a negative binomial distribution?
Negative binomial is not necessarily consecutive, right?
Absolutely, excellent, right? There are two crucial differences. The first one is that negative binomial has this kind of pattern, right? Let's switch to 0, 1 now. 0, 0, 1, and then 0, 0, 0, 0, 0, 0, 1. That's a negative binomial, right? But notice, as far as tracking two consecutive ones is concerned, we're not done here yet. In fact, we're not even started, right? Because we don't have consecutive ones. In fact, right, if we track for consecutive ones, we could have a bunch of things like this. We can have a bunch of ones right before that, right? Until we see a 1, 1. Right? So these are not connected, right? They track different phenomena. One is to find the second success, second single success, right? So to be sure, the negative binomial is also a stopping time, but it tracks a different pattern. It tracks the second ones to appear. But now we want a tracking that track a double ones, right, appearing consecutively. We understand? So it's a new problem. All right. So now, right, let's think. If I want to find expectation of N2, and given the theme of this problem, right, this lecture, sorry, we're almost out of time, but let's try. What do you think we should condition on for N2 here? What is a random variable to condition on to find expectation of N2? And this goes into the theme of, right, finding the right random variable to condition on. What is y?
I would guess N1, but I don't know if that simplifies the problem.
You hit on the right point right away. Actually, if you have guessed it's the result of first trial, that'll be wrong. All right, but if you say it's N1 is excellent. And I want to distinguish that, right? Do you see why if you condition on the result of first trial is not good in this case? The reason is, right, if the first trial is a failure, okay, that's clear, right? Then you just redo. So that's going to be N2 tilde. That's clear, correct? If the first trial is a failure, you just redo. The nasty part comes in when the first trial is a success. Then what does this look like? You see? Because you see now intuitively, now you have to say, okay, if the first one's success, now I have to look at the second one to decide. Correct? So that's not very elegant at all. So condition on the first trial doesn't seem like the right idea. Now, okay, so what about condition on the first two trials? Is that any better? Well, you think about it, not really, right? For example, first two trials have 0, 0, 0, 1, 1, 0, 1, 1, right? If it's 0, 0, you redo. If it's 1, 0, you also redo. Because you have a 0 here, so you cannot have a consecutive ones. If it's 1, 1, then the answer is 2. Right? But if it's 0, 1, what do you do? You understand? Then you want to look at a third trial. It never stops. Yes? Okay. And you see, right? What's the way to break, right, this kind of like issue? So the right analysis, right, to break away from this, right? And you see, the problem you see when we do these things is that, right, you might have a ones before this one or not, right? You might have a 1 before this one or not. That causes a problem, right? Once you have a 1, the one before might make it into a double ones or not. So basically what you're doing here is these y's don't give you the right information or not enough information or whatever. Not the right information. I know I'm out of time, but let me just kind of top of this real quick and we'll continue next time. If I condition on N1, right, what does N1 look like? N1 actually is a random variable, so I don't know, right, what N1 is exactly, but I know that if I have N1, then I have all zeros before that, right? So then I can look at the one after N1. So it will be, right, N1 plus 1 with probability P. Because, right, if I have N1 and I have a next one to be a success, I'm done. Or if I'm not a success, meaning I'm a failure, then I will repeat. You understand? And the reason why N1 works is because N1 gives you just the right amount of information, meaning that you know that by N1, you have a ones and all the ones before it is clean, meaning zeros. So I know exactly what I'm dealing with, right? Condition on the first number of the first trial, the first two trials won't yield the right or the nice recursion that we want. Okay, so that's actually demonstrating the idea of conditioning on the right random variable. Okay, so all right, let's continue with this on Wednesday. Okay.
Thank you.
Thank you, Professor.
Sure.
Thank you.